Hello. So in this section, we're giving a brief non-calculus introduction to exponential functions. I think just because this is a bit on the borderline of material that we can assume that everyone has seen in high school. It's possible that this is just new to some students. Having said that, this class isn't replacing a college algebra class. It's covering different material. So we'll only present the material in the section that we need to start taking derivatives, essentially. So exponential functions represent constant percentage rates of change. We can also think of them as repeated multiplication. So suppose you have a quantity Q, and this quantity increases by 2%. Well, increasing by 2% is the same as being multiplied by 1.02. Which is why we have these two sort of visions of the exponential function, because increasing by a percentage and multiplying by a number are the same thing. So let's say this increases by 2% every year. Then it's multiplied by 1.02 every year. So we start with a quantity Q. Let's call that year 0. After 1 year, we have Q times 1.02. After 2 years, we multiply by 1.02 again. So we have the starting quantity times 1.02 squared. And of course, we have this 2 representing 2 years, and then q times 1.0 to the second power. We see 2 again, and this is no coincidence. After 3 years, we'll have q times 1.02 cubed. And after x years, we have q times 1.02 raised to the power of x. So in general, if a quantity increases by, let's say R% every time interval, then after X time intervals, the amount of the quantity, let's say we started with capital Q, the amount of the quantity after X time intervals is going to be the initial value, Q, times 1 plus R to the power of X, where R is no longer a percentage. R has been converted to a decimal. And we remember that to convert a percentage to a decimal, we move the decimal place twice to the left. So, for example, 17.0% written as a decimal becomes 0.17. So, let's say an investment of $2,000 increases in value by 5% every year. Its value after X years is, we can use V for value, V of X is 2,000 times 5% is 0.05. 1 plus 0.05 is 1.05 raised to the power of X. Um, up here, I use the word increases. If a quantity Q increases by R% every time interval, etc. We can also have exponential functions where the quantity is decreasing. And if the quantity is decreasing, that's represented by a negative R. So, a boom, let's say just a mining town, has a population of 5,000 people. After the gold runs out, the population decreases by 37% every year. So here, because the population is decreasing, R is negative. 0.37. And after t years, the population is P of t equals the initial quantity, 5,000, 1 plus a negative 0.37 is 0.63 raised to the power of t. And for this applied calculus class, that's really all we need to know about exponential functions. I guess it would probably be also good to know what their graphs look like. So all exponential functions fall into basically one of two categories, depending on whether r is positive or negative. So depending on whether the function is increasing or decreasing. An exponential function where the quantity is increasing looks like this. So there's a horizontal asymptote of 0 in the negative direction. In the positive direction, so this is increasing concave up. So initially, let me maybe change this 0.9 to a 0.1 for emphasis. Initially, this exponential function might not be growing very quickly. It's increasing, but it's not increasing quickly. Because it's concave up, however, it eventually starts to pick up steam and increase very quickly indeed. So potentially slow initial growth, followed by extremely fast growth. By contrast, if we have a negative r, you see it's now a decreasing concave up function. So it initially decreases very quickly. Wrong way, zoom in. It initially decreases very quickly, but then the rate it's decreasing at slows down. Quick decrease, slow decrease. And sorry, that's that. This really is probably all we need of exponential functions to be successful in this course.